Hey there folks, In the last video, we installed the rear panel grid that not only covers up the unsightly elements of the frame, but also provides a consistent mounting surface for the cables that will be made in this video. Speaking of cables, we also attach the power panel that will organize the wires as they travel from the power supply to the frame's rear panel. Next, I detailed my thought process for how I go about choosing the wire I use in a build, and then use that information to crimp and install the GPU and motherboard power cables. To conclude the segment, we ran some thermal imaging tests to see how well the wire and crimps performed under stressful situations, and I was pleased with those results. In this video, I'm going to install the EPS cables, convert the pump's Sata connector to a 4-pin Molex connector, and build a wire harness out of Ethernet cable to connect an external front panel. I'm sure this entry in the series will be more amazing than a real deal 4-wheel ORV with bullets flying all over the place. So let's get this thing done. Behind the scenes, I made two 8-pin EPS power cables. I used the same tools and crimping techniques demonstrated in the last video when making the 24-pin motherboard power cable. I used the SN28B crimpers set to torque position 4, 17-gauge wire, and long-wing female ATX PCIe EPS pins. The wires were then inserted into 8-pin connector housings that are typical for EPS cables. Both of these cables are roughly 17 inches long. The EPS pinout for the NZXT C1200 power supply is as shown here. I'll also be using 180-degree angle adapters for these cables to keep the routing nice and tidy. The adapters I'm using have a plastic outer body, good solder joints under the hood, and a relatively low profile compared to some other angles I've used for this purpose. The EPS connectors on the motherboard are located at the top right corner of the CPU socket, so I'll start by plugging an angle adapter into each of those connectors. From the back of the frame, we now have a straight shot for the EPS cables to connect through the frame metal. To secure the EPS cable wires to the rear panel, I'll be using these simple clasps. They attach to the panel grid with an M2.5 by 6mm screw. On the left are three optional wire channels that are 1.4mm wide and 5.8mm deep for fan and front panel wires, and the four channels on the right, which are 2.05mm wide and 8mm deep for the 16 EPS wires. Each outside wall is 4mm wide, 6mm long, and have an M2 threaded hole for mounting the clasp cover. I'll use an M2.5 6mm screw to attach the clasp just above the power panel area. Now I'll attach another clasp above this one. The design of this second clasp is slightly different and only has channels for the 16 EPS wires and the 4 wires that will provide power to the left side fan hub. I'll attach this clasp to the grid with another M2.5 by 6mm screw. Here's how they line up once attached. From the front of the frame, I'll push the CPU end of the first EPS cable through the opening on the panel, and insert the other end into the 8-pin plug on the power supply that is closest to the frame metal. I'll now organize the individual wires into the grooves of the power panel. I don't have a defined process for this step. I simply stack them in whatever order results in the cleanest looking outcome. The grooves in the power panel can hold 2 wires each, so 4 grooves will be used for each EPS cable. On the rear of the frame, I'll now insert each wire of the first EPS cable into the channels of the first clasp, making sure to leave an appropriate bend radius on the wires as they come through the power panel. I strive for a 12mm bend radius, which I'll validate using a millimeter ruler throughout the mounting process. Before I insert the wires in the second clasp, I'll plug the CPU end of the cable into the 180-degree angle adapter, bend the wires back to form a smooth curve, insert the 8 wires into the second clasp, and then attach a cover plate using M2 6mm screws. With the first cable in place, I'll repeat these steps again to install the second EPS cable. With both cables situated, I'll cut strips of Velcro cable wrap and put it around the wires just before the curve, and put the other cover on the clasp just above the power panel area. Here's how both cables look as they pass from the front of the frame to the back, and here's how they look coming out of the power supply once Velcro wrap has been added. Now that the EPS cables are finished, let's make the 4-pin PWM cable that will power the 6 remaining radiator fans. I'll use the exact same tools, techniques, and materials shown in the 5th video of this series that demonstrated how to make 4-pin fan cables. That includes the PWM 2030M micro connection crimpers, 24-gauge stranded wire, female fan pins, and a 4-pin with 3-pin locking latch connector on each end. The cable itself is roughly 15 inches in length. I'll attach one end of the cable onto the 4-pin header labeled sys_fan2, loop the cable over the EPS angle adapters, push it through the same hole as the EPS cables, and once in place I'll add a small 4-inch zip tie to prevent unruly wire behavior. From the back of the frame, I'll thread the cable behind the EPS wires, remove the clasp cover, and stack all 4 wires into the remaining channel on the left side of the clasp. Now I'll very gently pull on the wires for a nice looking loop and then reinstall the cover. Moving on down the line, I'll remove the next clasp cover, set the wires in place, loop the connector around to the fan hub input header, and reinstall the cover. For good measure, I'll add 2 4-inch zip ties on the loop and snip the excess with flush cutters. Here's how everything looks with this cable installed. To secure the pump cable, I'll be using this simple clasp that has a 1.75mm wide by 3.5mm deep channel, which perfectly contours the 2 wires in the pump cable. I'll use another M2.5 by 6mm screw to attach the clasp to the grid and situate it pointing toward the distro plate. Next, I'll insert the cable and attach the tiny cover using M2 6mm screws. I've never really been a fan of SATA power connectors on anything but hard drives, so I'm going to take the opportunity to convert this cable to a 4-pin Molex connector. I'll use the flush cutters to snip the wires just behind the heat shrink section on the cable. Now I'll snip between and separate the red and black wires about 1.5 inches. To strip the wire ends, I'll use the Knipex auto strippers that I've used in previous videos and remove about 3mm of insulation. Using the SN28B crimpers on torque position 4, I'll attach a male Molex pin on each wire, and then insert the red wire into position 1 on the housing, and the black wire into position 2. The pinout on a 4-pin Molex connector is 12V on pin 1, common ground wires on pins 2 and 3, and a 5V wire in position 4. Since the pump only uses the 12V and a single common wire, I'll leave pins 3 and 4 on the connector housing empty. Now I need to make the cable that will connect the pump to the power supply. I'll be using 17-gauge wire, a 6-pin power supply connector, and a 4-pin female Molex connector. The pins I'll crimp for the power supply connector are the long wing ATX PCIe EPS pins we've used previously in this series, and the female Molex pins are part of the commercial Mate & Lock series. Typically, I'll purchase these in bulk from Mod DIY, but they can also be purchased from Mouser, DigiKey, Amazon, etc. When using the NZXT C1200 power supply, the pinout diagram for this cable is as shown here. This cable is crimped using the same techniques demonstrated in the motherboard cable crimping segment of the 6th entry in this video series. Once the individual wires are made, I'll insert each pin according to the pinout diagram. Next, I'll attach another clasp in this position using an M2.5 6mm screw. This clasp has a channel for each of the 4 wires it will hold, as opposed to stacking on top of each other like in other clasps. This is purely a design decision that helps keep the profile of the connector flat against the surface of the grid. I'll attach another of the same clasp at this position. From the back of the frame, I'll push the 6-pin connector through the power panel and plug it into the power supply. On the other end of the cable, I'll insert the male plug into the female receptacle, position each of the 4 wires into the clasps, and add the covers using M2 6mm screws. Here's how it looks once the cable is connected and routed. At this point, I'm going to start assembling the components that will allow me to have 2 front panels for this machine. For clarity, I define a computer's front panel as a device that has a power button, reset button, power LED, and hard drive LED. The first component we'll install is what I like to call the Ethernet toilet. This is simply a bracket that has 2 mounting arms and a larger square body that allows a U-green Ethernet coupler to slide tightly into. To permanently affix the bracket to the coupler, I'll fire up the mini hot glue gun and run a bead of glue along each edge on the coupler, except for the front edge. This is purely an aesthetic choice. There would be no harm in hot gluing the front edge as well. After the glue has had a chance to harden, I'll attach it to the frame in the upper left corner of the grid using M2.5 10mm screws. Now I'm going to install the wire clasps that will route the front panel wires on the grid surface. These clasps have 4 channels that will each hold 2 24-gauge wires. The 8 wires in total will bring function to the power and reset buttons, as well as to the power and hard drive LEDs. I'll install one of these clasps in each of the marked locations with an M2.5 6mm screw. We're now ready to install the harness, but we haven't made it yet, so we'll do that now. I'll start by cutting 8 lengths of 24 gauge wire from the spool that are 39 1/2 inches long. Next, I'll cut a piece of Cat5e Ethernet cable from its spool that measures 8 to 10 inches long. I'm using solid core Ethernet cable here, though it would actually be better to use stranded Ethernet for this task I'm about to demonstrate. But I don't keep a lot of that stocked and reserve it for special use cases. Solid core will work just fine, since this harness won't move an inch once it's completed. Using a Sharpie and ruler, I'll put a mark 2 inches in from an end on the Ethernet cable, insert the cable into my Klein crimper and wire stripper, spin the cable so the razor makes a cut into the outer jacket, bend the cable at this mark and pull the jacket off the wires. Next, I'll use the flush cutters to cut off the exposed ripcord. Unlike traditional Ethernet cables that are made with specific wire color ordering between patch and crossover cabling, I'm simply going to be ordering the pairs next to each other for simplicity. Therefore, each color and corresponding light or white color will be next to one another. I'll untwist and straighten each of the individual wires like you would when making a typical Ethernet cable. After they've been straightened out, I'll use a millimeter ruler and Sharpie to put a mark 30 millimeters back from the end of each wire. Once they've all been marked, I'll use my Klein curved strippers to remove the 30 millimeters of marked insulation on each wire, leaving bare copper to work with. Now I'm going to prepare the 39 1/2 inch lengths of 24 gauge wire for splicing. Using a ruler and pencil, I'll put a mark 11 1/2 inches from one end of each wire. With those marks in place, I'll use a millimeter ruler to put another mark 10 millimeters beyond the mark at 11 1/2 inches. At these two marks, I'll use the 24 gauge slot on the Klein wire stripper to cut through the insulation, and then I'll grip the indentions with my fingernails and give it a little pull to create some separation from the remaining insulation. In a past video, I showed one method that can be used to slice back a flat edge of the insulation, and today I'll use another method. I'll hold the razor like a pencil, carefully insert the tip into the insulation, and then pull the razor tip from indent to indent. Now I'll bend the wire toward the cut, grab the edge of the insulation that flares out, and pull it free from the wire. As I go through this process, I'll inspect the strands closely to ensure that I didn't cut any. If I see that I have, then I'll make a new wire. With the Ethernet fragment ready and the 24 gauge wire prepared, it's time to splice them together. To do this, I'll hold one of the Ethernet wires parallel to one of the 24 gauge wires, with the shorter end of the 24 gauge length pointing the same direction as the Ethernet strand, and then tightly twist the solid copper of the Ethernet wire around the 24 gauge wire strands. On the last twist, I like to have the copper form a small angle that overlaps with the 24 gauge insulation about a millimeter. I'll show you why I like this in just a second. Splicing wires in this manner will not yield as strong of a mechanical connection as, say, a Western Union splice, but I've tested the resulting strength of this connection after soldering, and it's near the break strength of the 24 gauge wire on its own, so it's more than fit for the purpose at hand. Let's take this out to the shop and solder the connection. I've set the wire up in the helping hands and have the tip cleaning station, 6337 rosin core, 0.8mm solder, and an 80-watt soldering iron ready to roll. These are the same tools and materials we've used to solder things together in past videos in this series. When working with small wires like these, I try to localize the heat to just the area that needs soldering to prevent as much insulation melt as I can. A small tool that helps me do that are these toothless, flat-billed alligator clips. The front jaw width of these clips is 2mm wide. In terms of placement on the wire, I like to have roughly 1mm of the clip on the wire and 1mm on the insulation. The reason for the short length of overlap between the solid copper wire and the 24 gauge insulation is so that when the heat builds in the alligator clip and the spring pressure flattens the existing insulation, it will be squeezed around the end of the copper wire, and once it hardens, will provide a tiny bit of strain relief for the 24 gauge wire strands. That's what I tell myself at least. Bear in mind the clips are steel-plated copper, so if I'm sloppy with my soldering technique, I could actually solder the alligator clips to the wire, and that would be very anti-good. With a clean iron tip and a drop of solder to help with heat transfer, I'll press the iron to the bottom of the wire, gently run the solder back and forth a couple of times, and remove the tip of the iron. Now I'll remove the alligator clips, remove the harness from the helping hands, and we can see how the plastic has fused around the wire angle. There's minimal melting otherwise, and the solder itself has a nice shiny appearance, indicating a low probability of a cold solder joint. Good enough for government work. Now it's time for some heat shrink. I'll use a millimeter ruler and Sharpie to put a mark 10 millimeters back from the edge of the soldered wires. Next, I'll slide a 30 millimeter long, 1.5 millimeter diameter heat shrink fragment over the wire, push the edge of the heat shrink to the Sharpie mark, and then use a heat gun to evenly melt it in place. That's 1 wire down and 7 more to go. Here's how things look after all 8 wires are spliced together. Before closing the splices up for good, I labeled each wire's color according to the Ethernet strand color on each end of the 24 gauge wire. Finally, I'll slide a 30 millimeter long, 3/8 of an inch diameter, adhesive lined section of heat shrink, position it directly on top of the smaller pieces of heat shrink, and melt it into place. The custom harness portion is now complete, but I need to add a Cat 5e plug on the other end. The wire color order, once inserted, will be light orange, orange, light green, green, light blue, blue, light brown, brown. I'll strip the jacket, clip the ripcord, straighten the wires, clip the ends with the flush cutters, validate the color arrangement, push the wires through the connector, and crimp using the Klein Tools pass-through crimper. Being a pass-through crimper, the excess length of Ethernet strands will be cut off with the crimping action. Next, I need to validate the order of the front panel pins on the pass-through box. I'm not as concerned about the power and reset buttons, as those are simple bridge connections and it really doesn't matter how they are hooked up. The LEDs, on the other hand, have a positive leg, or anode, and a negative leg, or cathode, that need to be hooked up correctly to the positive and negative wires from the computer for the light to function. To perform this validation, I'll use a multimeter. I'll turn the dial on the multimeter to the 2 label in the DC voltage measurement section, which I apologize is hardly readable given my noobish camera focusing skills. With the computer turned on, if I hold the probes on the pins for the power LED, and I see the letters OL, this means that the measured voltage is greater than the selected measurement range I spun the dial to on the multimeter. This results in the multimeter screen showing OL for overload or over limit. This is what I'd expect to see, knowing the output voltage of this LED is 3.3 volts. I'll turn the dial once more to the up to 20 volt measurement option. If using an auto-ranging multimeter, selecting the right range is a non-issue, since the unit would automatically determine that based on the reading itself. Now when I press the probes onto the pins, rather than seeing the OL abbreviation, I see 3.3 volts being measured. This is important for 2 reasons. The first reason is we now know the voltage on the power LED pins, and we also know which of the 2 pins I'm pressing against is the positive and which of the 2 pins is the negative. We know this because the multimeter does not have a negative sign in front of the voltage measurement, which would indicate reversed or negative polarity. Let me switch the positions of the red probe and the black probe. Doing so still shows the 3.3 volt measurement, but it also has the negative sign appear in front of the reading. This means that the red probe is where the black should be, and the black probe is where the red should be. Or in other words, they're reversed on the pin pair. I use this method to verify lots of small electronics work where I run pairs of wires but neglected to put a label on the pair telling me which was the positive and which was the negative. It would be much simpler if I just used colored wire to begin with, but what can I say? I prefer all black wire most of the time. After testing both LED pin pairs, I have rediscovered that the positive lead is on top of both pairs, so the full pinout of the pass-through box is referenced as so. Knowing the orientation of the wires, I can now install the custom wire harness. But wait, there's one more clasp to install. This is a simple 2-post clasp with a 9mm by 9mm clamping area that is used to loosely hold the harness in place. Using an M2.5 6mm screw, I'll attach this clasp just above the left side fan hub, position the harness, and attach the cover plate using M2 6mm screws. I prefer to make this cable a little longer than it needs to be, so I'll curl the excess around in a little loop and insert the Cat 5e plug into the bottom of the Ethernet coupler. To ensure the loop stays put, I'll add a 4-inch zip tie, lightly cinch it down, and trim the excess with flush cutters. In terms of position, I'll turn the harness so that the black 24 gauge wires are angled toward the pass-through box on the other side of the frame, since that's the direction those wires will be routed. Next, I'll drape the wires over the top of the EPS wires, and the top of the distro plate fittings. Now I'll insert each wire into the channels of the clasps, starting from the Ethernet coupler all the way over to the pass-through box, adding the clasp covers as I go. I'll stack each wire pair together, so light orange and orange, light blue and blue, etc., with the light wire on the bottom of each stack. Here's how things look with all of the wires inserted and the covers added. Prior to securing the wires in the clasp, just above the pass-through box, I'll strip 2.5mm of insulation and use the PWM 2030M crimpers to crimp a 2.5mm female Dupont pin on the end of each wire. With all the pins crimped, I'll insert them into the labeled connectors, starting with the bottom 2 pins on the pass-through box, which are for the hard drive LED. For consistency across these kinds of cables, I always assign the solid color wire to the positive leg of the pin pair. So, since I'm working with the light brown and brown wires currently, the positive pin for the hard drive LED will be the solid brown wire, and the negative pin will be the light brown wire. I'm also double checking the alignment of the wires to the pins, because I want the labeled side of each connector to face toward the distro plate. Once the hard drive LED wires are hooked up, I'll move on to the power LED, which will have the solid green wire going to the positive pin and the light green wire going to the negative pin. As I mentioned earlier, the power and reset button wire color assignments don't really matter since they will lead back to a momentary push button, but the color arrangement will be blue and light blue to the reset button, and orange and light orange will go to the power button. Here's how all the wires and connectors look on the pass-through box once complete, with a couple of small zip ties added for good measure. The end-to-end path for the harness is as shown here. On the other end of the harness, I'll loosen the screw on the clasp just below the power panel area, spin it to point up, and retighten the screw. I'll sort and insert each wire into the clasp channels, and then add a cover using M2 6mm screws. Since I want a nice downward turn for these wires, I'm going to install one more clasp to the grid using an M2.5 6mm screw. Once all the wires have been inserted, I'll add a cover to the clasp to lock them into place. The twists and bends along the path the wires have taken has resulted in a few being longer or shorter than the others. I'll bundle all the wires together, and using the flush cutters, snip them so they are all once again even. Using the Klein wire strippers, I'll take 3 to 3.5mm of insulation off each wire end. Now I'm going to crimp 2.54mm male Dupont pins on these wires, using the same methods I demonstrated in a previous video for the female Dupont pins, including leaving the cut tape fragment on the pin during crimping. My crimper of choice is once again the PWM 2030M, using the second jaw die and torque dial position 4. To remove the tabs off the back of each pin once they've been crimped, I'll use the mini needle nose pliers to pinch the tape reel fragment and twist until it snaps free. The pinout specified when making the connections at the pass-through box will be followed here as well. For the positive wires on the power and hard drive LEDs, I'll insert those pins into the connector housing lane that has the small arrow. This will help me keep the wiring straight once these wires have something to plug into a little bit later. Also, as I finish inserting the wires into their respective connectors, I'll use the flush cutters to snip the tape label and peel those off each wire. And that's as far as these wires are going to go for now. We'll come back to them later once the SSD rack is installed. This is a good spot to put a bow on this segment. With the harness in place, we're ready to build out the front panels and install the SAS HBA cabling. The next segment won't take long to post, but just how long is largely dependent on how engaged I am in the second game of the ALCS tonight. So we'll see if I get it posted tonight or tomorrow. I hope you've enjoyed this demonstration. Thanks for watching, and out.